where we left off with this problem, we had just finished solving for w in our reduction of order problem. And now we're at the point where we need to undo the reduction step because the thing we want is y2. To get y2, we need u. And to get u, we need a w, which we now have. So we're going to remember that we introduce w as u prime, so u is the integral of w with respect to x. That means that u is the integral of c x to the minus 6 dx. And so when I integrate that, I'm going to get c over minus 5 x to minus 5, just integrating my power rule. And again, showing that issue that can happen with constants, maybe I add plus a constant here. But I definitely have u. It's something I could plug into WebWork. I'm pretty happy. And then from here, the reason I wanted u was to give me y2. So since y2 equals u times y1, now we know, I'm going to do a little arrow to make me feel like stuff's happening. My u was that negative c over 5 x to the minus 5 plus k. And my y1, way back at the start of the problem, was x squared. So I got to plug that in too. And at this point, I've found y2. I'm gonna real quick show you like how you would say what y2 is, and then we'll put it into the general solution. Because sometimes you all simplify here and sometimes you simplify at the end, and I want you to see both. So in this case, suppose I say, great, I've got c over 5 x to the minus 5 x squared plus k x squared, or negative c over 5 x to the minus 3 plus k x squared. I say, that's my y2, I just found it. The thing is that when you find y1, y2, you want them to be those linearly independent things, and an immediate way to break linear independence is to have a term that looks just like the one you started with. So really, if you wanted to write like the fundamental solution set, or to say only what y2 is, at this point, you would pick out the function that's new to you. So you would say, oh, y2 must be x to the minus 3. I ignore my constants, I ignore the things that look like my y1, and I just tell you that I found x to the minus 3 must solve this differential equation. If WebWork asks you just to put that second solution, that's what you would put, not this whole thing. Alternatively, we can get to the same place by plugging everything into the general solution, which I'm going to do next. But as you can see, I need more space, so please pause if you're still writing. Well, I will say real quick, from y2 equal x to the minus 3, then you could say, great, my y must be c1y1 plus c2y2, so I guess that's c1x squared plus c2x to the minus 3. And then you would get your general solution for that case where you simplify first and then move on to the general solution. Or when you're at this point, you might jump right to the point of plugging into your general solution. So then you would say, okay, I guess that means y is c1, y1 is x squared, plus c2, y2, which I just found. I guess I'm going to make these k's because I've got a c1 over there. negative c over 5 x to the minus 5 plus c1 x squared. Sorry, I think I'm missing. Yep, my bad. When I copied this down, I just forgot to put the minus 3 there. Minus 3 there. So, make sure you fix that power if you copied it down wrong with me. But if this is the general solution you have, then you have to make the simplifying step here where you turn it into only one constant. And the way you do that is just going to be by grouping like terms. So I've got k1 plus k2 c1 x squared. There's my x squared term. There's my x squared term. And I've got negative k2c over 5 x to the minus 3. There's my x to the minus 3 term. And here's where you would just say, I treat these like their own new constants. c1 x squared plus c2 x to the minus 3. And in your skeleton notes, I wrote those as A and B instead of K1 and K2. I'm sorry about that. I'll just go back and edit them, I guess. Ignore what I just said. It's fixed by the time you look at this. But in either case, the first way where you simplify then plug in, or where you plug in then simplify, we do end up where we have only one constant for each part of our fundamental solution set, or only two constants for the second order problem. So, great work. We're sitting here at about 7.5 minutes. So by the tally I've been keeping, we're just over 50 minutes of this lesson. And this lesson is so overwhelming that I don't want to spend a full 60 minutes on it, because I know that you all are probably exhausted after that general problem. In your skeleton notes, you've got a section on verifying solutions, and you can do it if you want to. It's just practicing again the stuff that we covered when we first introduced higher order problems. But I'm not going to work through those steps, so you can leave them blank, or you can do them in your own time when you feel like you have rested enough from reduction of order. Instead, I'm just going to tell you all the takeaway right here that I really need you to know, which is that you could go ahead and verify that this set we just found, x squared x to minus 3, is a fundamental solution set. For our ODE 0 equal x squared y double prime plus 2xy prime minus 6y. You have the tools to do that from early in this section. And doing it might make you feel better about this whole process, like more confident, like, oh, reduction of order really does something. But you do not need to do that every time you work on one of these problems. You can just accept that reduction of order is always going to work. We're always going to have something that's a solution, because that's how we start out by setting up the problem, is by ensuring that it's a solution. And it's always going to be linearly independent. It's just like cool magic in the reduction of order problem. So I'm going to go ahead and stop us here. But great work with reduction of order. I know it's a hard one. I'm pretty sure you're going to like everything we do in this section more than this. So kind of the hard part's over.